Hey guys, how's it going? This is Siri and I'm back with another PyTorch video, and we're going to be continuing our discussion on PyTorch's automatic differentiation engine, AutoGrad, and slightly move on to using the different optimizers that are available that PyTorch provides for us. Okay, so we are going to be talking about optimizers today. And in our example, our linear model, right, we have an input and we have an output, forgive the noise, we have like y equals mx plus b, and we want to find the perfect slope and the perfect y-intercept that will best model and represent that data. So if the relationship between the input and the output was like y equals 4x plus 3, and our initial guess was y equals x, right? Because the weight is going to be initialized to 1, and the y-intercept, or the bias, is going to be initialized to 0, and we're going to be updating them iteratively. And we've talked about that entire process in the past, like 5 or 6 or 7 videos. And I would definitely recommend going through that. But in this video, we are going to sort of check out the different optimizers PyTorch provides for us, other than, the gradient descent that we've implemented ourselves. So what gradient descent does, as we've discussed, is that it takes a look at the loss, which is the difference between the predicted value and the actual value, and we take the derivative of the loss, which just tells you how far off you are, and you take the derivative of that with respect to your parameters. And so that's what we're trying to optimize the parameters by using this derivative and multiplying it by a learning rate, and then that learning rate times the derivative is going to be the update that you make to the parameter. And we're going to do that iteratively. We're going to do that like every single time throughout our loop, so that it actually models our data and so that we can minimize the loss. So we want to be as close as possible to the actual value. So that's what we did for our linear example, and that's what gradient descent is. That's the gradient descent algorithm. We try to find the minimum of the loss, whatever it is, try to find the local minimum using our calculus and using our chain rule and back propagation, you would say in like machine learning terms, and find the best slope and y-intercept, find the best weight and bias for that model that best represents our data. So that's the gradient descent algorithm. But, in most cases, our relationship isn't always going to be linear. I mean, we are definitely going to be dealing with linear components in our crazy mathematical web when our inputs and outputs aren't so, obviously related. I mean, they are definitely, they have a pattern, but it's hard to distinguish that based on just the y equals mx plus b alone. And so when we have more complicated models, that isn't just like a best fit line, and we have so many other like variables that are impacting the output, so we have to look at a lot of other things when checking out the relationship between the input and the output. When we have to do those complicated things, gradient descent isn't gonna help us that much. Okay, so we need more options for our optimizers. And so there are different ways to optimize a function than just taking the local minimum and making updates to our parameters based on that and based on the learning rate. And we've talked about all these different components. If you're kind of confused, then you should definitely check out my other videos that go into each of these parts in more detail. Okay, but for now, let's look at the different optimizers that we can use. And so if we want to take a look at that, then we can import the torch module, and there is an optim submodule within torch, okay, where we can find the different classes implementing these different optimization algorithms. Okay, so like I said before, gradient descent might not be the best optimization algorithm for every situation, so we should check out some others. Okay, so we can say import torch.optim as optim, and this dir stands for directory, and we can pass in optim, and we can see the list of classes of these different optimizers and optimization algorithms. Okay, and each of these classes implement their own optimization algorithm. So we see atom here, we see like SGD, stochastic gradient descent, and other stuff. Okay, and let's keep some things in mind. Okay, a couple of things in mind. Every optimizer constructor. Okay, so first of all, we have some things called optimizer objects that do this sort of optimizing work for us. So instead of, implementing our own sort of updating here, the optimizer will do that by itself. Okay, so for every optimizer object, it has a couple of these properties. Okay, it can update the values of the parameters, because that's the whole goal, right? To best model the relationship between the input and the output. That's what we need. We need to optimize the parameters. And update the values. So, and we also need access to the grad attribute, which we have with optimizer objects. So the grad attribute holds those gradients for every iteration. And we've talked about accumulating grad functions, which we don't want to do. Okay, so we said that we need to make this grad attribute equal to 0 at the end of the iteration so that accumulation doesn't happen, which just means that you're adding the gradients of an iteration with the previous iteration's gradients, so you're adding them up and you're accumulating them and you're summing them up, which are not the numbers that we want. We just want the new gradients. We don't want it to be added to the previous gradients and return that as our result. So, we can access the grad attribute, and we can do those sorts of things where we can, like set it equal to 0, so that these crazy things and weird things don't happen. Okay, so so every optimizer constructor, okay, considering that we have an object, right, we need a constructor. So every optimizer constructor will take in, many parameters, and usually the first one is setting the grad attribute equal to true. The requires grad equal to true. Remember, we talked about it up here, where, where was that again? Yeah, here. So, what this just tells PyTorch is that, we're saying, hey PyTorch, I want you to keep track of all of these, of all the history of how a tensor came to be and how our parameters came to be, so that we can take the derivative of the loss and whatnot. So we need that tracking of the history of how tensors came to be, so that we can apply the chain rule and do some back propagation. So you need that in any case, right? We need those derivatives in that chain rule. So the first parameter is usually setting requires grad equal to true, and this will create an optimizer object. Okay, and there are also two methods that come with optimizer objects. Okay, these are just Python classes. So okay, this is exactly what you think it is. So, okay, two methods. So we have 0 grad, which is like zeros our gradients after like whenever you want automatically. So we don't need to, say like, oh, if params.grad is not none, params.grad.0, we can just, the optimizer will do that for us. I mean, we're still gonna have it in our training loop, but that's now the optimizer's job. Okay. And we obviously need to update values of those parameters according to the optimization strategy that we implement in this class, this optimization algorithm. Like I said, these are all different algorithms. These are all different strategies of how you can optimize the parameters and get the best parameters, minimize the loss. And so we can use something called step that will update the values of the parameters based on like how the optimization algorithm works, right? If it's gradient descent, then we're going to do whatever we did up here. When we, you get the point, right? There are different strategies for each of the different algorithms. So, yeah. Okay, good. So let's see first like how we can use gradient descent, because we did it manually above. Let's see what how we can implement it using PyTorch. So I think this is like the first part of like we're scratching the surface of the tools that PyTorch has to offer us, right? Up here we've used the basic building blocks, which were like tensors and trying to piece through this entire process together. But now we're like starting to talk about optimizers, and next we'll talk about like neural networks, and we'll get into this. We're almost there in like getting to the interesting tools that PyTorch has to offer us. So let's see. Okay, params is equal to torch.tensor like we did before, and just the weight is going to be 1, and the bias is going to be 0. Requires grad is equal to 2, true. Okay, the learning rate is how much we want to scale the derivative of the loss with respect to the parameters by, because we don't want to like subtract our parameters. We don't want to subtract this loss of the derivative of the loss with respect to the parameters from the parameters itself, because that's too large of a value. Actually, I don't need to write this down. We already did this above. So, yeah, if you want more insight into learning rates, I would definitely recommend checking out my video on learning rates, and you'll really see how it improves the process a lot, and the accuracy of our model. Okay, so now we're going to be defining an optimizer object. Okay, optim.sgd. Okay, and first we're going to be passing in params. Okay, and then LR is going to be equal to this variable that we've created here. Okay, so this is the gradient descent optimizer. We didn't import torch yet. Okay, good. Did we run? Okay, great. So now let's, redefine our TP. Actually, it's basically the same as TU and params, all of the params. And if you're confused, don't be, because this is just like an example that we started at the beginning, that where this is our prediction, our temperature prediction, and this is the unknown, which is basically the input, and we're trying to predict the relationship between the unknown unit and Celsius, which we've already done above, and you know, it was Fahrenheit, but now we're trying to get a more accurate result. So actually we're doing the same thing, because this is just SGD. So loss is equal to loss Fn, TP, TC. So we're not doing anything different, I take that back. But what we are doing is utilizing this optim.sgd. Okay, optimizer. .0 grad. I said that we can do that, right? So now that's going to be zeroing all of our grad, all of the values in the grad attribute, because, you know, we defined TP, we call the loss. We didn't call backward. Okay, so let's make it 0 first, and then let's call backward. Loss.backward. We'll put this in a loop eventually. And optimizer.step. Okay. This does the updating based on which algorithm we chose to use, which optimization algorithm we chose to use. And let's see what params looks like. Model's not defined. Okay, that's quite annoying. Okay, let's start from the beginning. Okay, inputs paired with outputs. Temperature conversion example where we have TU as our input, TC as our output. Model definitions. Loss function. Import torch. How do we change our parameters? How derivatives play a role in this entire process. Okay, good. So it requires grad is equal to true, and we get some values for our parameters. Great. Because we've, you know, it started out as 1.0 and 0.0. And now we've changed it. We've changed it after first of all, we have an output, we have a prediction. We pass it into the loss function, which takes the difference between the prediction and the actual output in Celsius and squares that difference. We are zeroing our grad attribute, even though there's nothing, even at the beginning, like grad is probably going to be, you know, when we run that again and we say params dot grad is none, we get true. So now it's not none. I mean, 1 second. Yeah, so yeah, now it's not none because we've called backward on it and now it's populated with values. So what happens when we put this all together? This whole new training loop, which we've done several times. We've, you know, copy pasted it after we've made some edits, and we'll see how it looks like now. Okay, so we have a training loop and epochs, learning rate, params, TU/TC for every epoch in range of the n epochs plus 1 because it's exclusive. So it seems like now we might be able to get rid of this part, right? Because we have an optimizer object that will do that for us. So we can just delete this for now. We'll add some more things in just a sec. So now we don't have a W and a B. what we have instead are just params. Argument unpacking here. Loss is just our loss. So now let's get rid of our gradient function that we've defined ourselves and start. Okay, so first let's start using our optimizer. First, at the beginning, what we saw was, if it's not none, then zero it out. We'll do that automatically here by saying optimizer dot zero grad. Just call that method. Okay, and we're all good. So now let's call loss dot backward. Okay, and let's update our parameters. Let's get rid of this now. And let's say optimizer dot step. Okay, because now we don't know how we're going to be updating our parameters. Okay, optimizer dot step, and let's keep that. Okay, honestly, it doesn't really matter where you put this as long as it's before the backward, because when you go through it a second time, you need to like make it 0 before you call backward again. So, and that's mainly because of the accumulation that's going on. So if you're kind of confused about that, you can go back and watch what that's all about. And so yeah, let's run that and let's call it. Let's call the training loop and say n epochs is equal to 5,000 like we did before. Optimizer this time is equal to, we didn't pass in optimizer as our, okay, n epochs, and we also want the optimizer. So this, when you create a function, we don't know, Python doesn't know what object is going to be passed in. It's assuming that it has a .0 grad function or method. So we need to pass in a real optimizer, which we've defined up here, which is an optimizer object. This is an optimizer object right here. And so we can just pass that in. And we actually don't need the learning rate because we're not using this, right? Because we're not updating the parameters ourselves. So yeah. Optimizer equals optimizer, and params equals params, and tu is equal to tun, comma, tc is equal to tc. Okay. Okay, wonderful. Okay, so it's at 29, but it works. And we can easily change the optimizer now because we don't need to change any of our actual training loop, because the only thing that we're changing is what kind of optimizer object it is. So you can change this SGD to whatever atom if you wanted to. So let's give that a try. Okay, run it. Okay, so you don't see that it's working as good as the SGD because we're having a much higher loss even after 5,000 epochs. But it's easy. That's the point. The point is to see how easy it is to just change what kind of thing we're using here and just run it and get different results. So that's pretty cool. and requires grad is equal to true, because if the original starting tensors requires grad is equal to true, then it's going to be true the entire way until you get to whatever result that you want and whatever updated parameters tensor that you have at the end. So yeah, I think that's all I wanted to talk about with you guys today. We've talked about optimizers, we've talked about the different kinds of optimizers, and we can see how we can, we have this list here, and so we've discussed how there are alternatives to just using the SGD that we've defined ourselves up top. And we've talked about the different properties of optimizer objects, how we can update values of the parameters and access the grad attribute. And you can set requires grad is equal to true as the first parameter, and we also, apart from these two properties, we also have two methods that we can call on optimizer objects, which are 0 grad and step, which updates the values of the parameters based on whatever specific optimization algorithm you chose. And we see this training loop implemented below, where we the new things that we've added here are optimizer.0grad, loss.backward, although that's not new because we've done that in our last video, and optimizer.step. Okay, yeah, I hope you guys learned something new today about optimizers and about AutoGrad and PyTorch in general. And I'm looking forward to seeing you guys in my next video, where we're going to be talking about the training and testing data sets. Yeah, for now, stay safe, stay curious, and don't forget to like, comment, and subscribe.